Hello everyone, and thanks for joining DataCon LA 2022. Welcome to the track AI ML Data Science. My name is Tanmay, your host, and she's Apurva. Please keep your phones on silent during the session and don't hesitate to raise your hand to ask any question. This session is currently streaming via Zoom and will be recorded. It will be available online in a few days. Today, we have our guest, Dr. Ash Pahwa, and he will be talking about the title Transformers for NLP. He is a PhD and affiliated with CalTech. Without further ado, I'll hand this over to the speaker and thank him for being here.
Okay, thank you very much, Tanmay. And all right, okay, so we are thinking of starting this session maybe just after 2 or 3 more minutes because there are other sessions going on in parallel, and it's a huge university, so some of the people are going to walk from different rooms to this room. So that's the reason they asked me just to delay it by a few minutes. So that's what the reason for the delay was. Okay, so we thought that we're going to wait for 5 minutes. So it's almost 4 minutes after 5. So I guess maybe we can just start right now. Okay, so what I'm going to talk about is transformers for natural language processing. So first of all, raise your hand if you have heard the word transformers. Okay, a lot of people, at least a few, at least half of the people know what a transformer is. Okay, so transformer is a new architecture that was proposed by Google in 2017. Okay, so what is the advantage of transformer? What is something new that transformer did, which were not able to do before? Okay, that is the focus of my talk today. Okay, so before we go further, so I'm going to start my talk with this. How to move forward. Frozen. Okay, now it's working. Okay, great. Thank you. Thank you, John. All right. Okay, so now let me start with this thing. This is the crux which I'm going to talk about. Okay, so let's test your English language skills first of all. So I hope everybody knows English. Yes, I see. Okay, so now suppose if I ask you this question. I went to a bank to deposit money. What is the meaning of the word bank? A is the bank where we go, or a bank of a river. What does it mean? It means A, everybody. Now, suppose I ask you another question. I went to a bank of a river to take a walk. What is the meaning, A or B? Answer is B. How do we know that? How would a computer know this thing? Computer says word bank, it's just going to pull out the embedding for the word bank. That's all. How can a computer tell the difference between these two things? And this is what transformer basically gives us. It gives us embedding based on the context of the word. Okay. And that concept is called self-attention. And attention and multi-held attention and a whole lot of other things like that. So that is something new that came about in transformer. So my talk is going to be basically how we do that thing. How do we determine these things? So that's what basically it is. So let's go back to my presentation from the beginning. So this is going to be the outline of my talk. Would be that what are transformers? Transformers, which are applications. There are 2 major applications which have come about, which are GPT and BERT. Okay, and then I'm going to focus primarily on the word bank because that is the example which I'm going to take. But of course, this thing is applicable to all over the place. Although we can do some context-sensitive embedding, but still it is not completely done yet because I can say in humor something. Suppose if I say, hey, come on, man, you are a fool. No, I don't mean that you are a fool. You just said, I'm kidding, How could you capture those things? Well, we cannot do that thing. Of course, we have reached for using transformers up to a certain extent, but we have not solved the problem completely. But at least it was the first step in the right direction. And our focus is going to be what that thing is. So let's see. So transformers, okay, first of all, just want to tell you about myself very, very briefly. In fact, currently I'm teaching. In fact, when I was hearing the speaker from the previous session, I was sitting in the last row over there, and he was emphasizing how important is the education. And that is the business in which I am in. I'm basically part of CalTech, so we teach these courses over there. So I teach machine learning, deep learning, and natural language processing, and all those kind of stuff at CalTech. So that's just my kind of a background. I've been affiliated also with UC Irvine and UCLA and UCSD. Okay, so yes, so we have so this is the outline of my talk. We're going to talk about what is the word, what is GPT, what is BERT, and what is the context sensitive embedding. So we're going to look into positional encoding and also self-attention and how this whole system basically works. Okay, so that is the outline of my talk. So transformers are the new family. It's a new architecture basically. Transformer is a new architecture which was released in 2017 by Google. And transformers basically replace RNN and also LSTMs. RNN and LSTM have become obsolete now. Okay, so they have been replaced by transformers. So now transformer has a two-layer architecture, which is an encoder and a decoder. And this is that very, very, very famous paper. This will go down in the history as one of the founding paper for area of artificial intelligence, because this basically introduced the concept of self-attention, which was not there before. Okay, so as you can see, do I have a laser? No, we don't have a laser, then never mind. Okay, just look at the diagram on the right-hand side. You can see that this diagram has taken straight from this paper. And some of you might have, who are already familiar with the transformer, must have seen this diagram a million times before. So on the left-hand side, you see a clear encoder, and on the right-hand side, you see a decoder. So the primary application of this thing was translation. That you feed on one side, you feed in English language, and on the other side, right on the top, you start getting a different language, possibly Spanish, could be French, could be any language you want to. So the primary application basically comes out to be translation. But not only we can use this thing for translation, we can also use for enhanced embedding. If you only take into consideration the left part, which is encoder, it can be used to solve the problem which I raised right in the very beginning, enhanced embedding. And on the right hand, and in fact, the BERT model is built upon the encoder part of it. So I'm sure that everybody must have used Google today. So I think that asking this question is pretty useless, because answer, of course, is going to be yes. Now the question really is that how many times you use Google today? The answer could be maybe 50 times, 100 times, or 500 times. The people like me could be 1,000 times. I check everything out. Now Google uses BERT. We are using BERT there. And that is the reason why Google has become so good. Okay, so earlier, 10 years back, Google used to be good, but now it will become very good. Or I should say very, very, very good. Why? Because of BERT. Okay, because of all the context sensitive stuff they are doing right now. Based upon the context of the word, they can understand exactly what to mean. And the same thing is also true for Siri. As you know, Siri we have in our iPhone. We have Siri and also Amazon Alexa. I hope there is no Amazon Alexa around here. It will just gonna wake up if at the moment I say the word Alexa. So all these things, all the robotic stuff is all happening because now the robots have the ability to understand the semantics of what we are saying. And this is very important. Okay, so as I said before, Google, of course, uses BERT in the search engines. And that is the reason why a Google search engine has become very powerful. And there is another language model which has come out, which is called GPT. GPT came from OpenAI. GPT is not a Google's product. A GPT is a product of OpenAI. And OpenAI is another company in San Francisco. And the reason it is very famous for is because Elon Musk is also invested in that company. So because of that reason only, it has become very popular. But so they came up with GPT-1, GPT-2, GPT-3. Okay, so all these kind of new language models are coming out. So these things are all, both of them, BERT as well as GPT are based upon the transformer architecture. So these are the three very, very important papers which came out for my GPT-1. GPT-1 came out in 2018, GPT-2 came out in 2019, and GPT-3 came out in 2020. So now the question would be that, do you think we are also going to get GPT-4, 5, 6? My guess is not, because we have reached the threshold now. We have reached the saturation point now. And there is a lot of debate going on in this industry, whether by adding more number of parameters in my language models really helps us to make it a better language model. Some people believe that's not the case. So I very seriously doubt we're going to see GPT-4, GPT-5, GPT-6 of this type. We are reaching a kind of a saturation point. But itself, so one of the kind of great things about GPT-2 is that GPT-2 has the ability to generate text. GPT-2 can become the next Shakespeare, write poetry. Isn't that mind-boggling? That it's going to generate text. So now suppose if you want to generate some news story, so you just give them a few words, it will generate a news story for you. So that's amazing. But of course, some human has to check that thing if that news story is correct or not, or how accurate that thing is. But yeah, system has the ability to kind of generate text and generate poetry. And we are basically reaching at a point that we are building almost a kind of human robot. Robot can, of course, have feelings. As you know, some of you might have heard about that. Google language model is sentient. Some of you might have heard that story, which became so controversial. And now, in fact, Google has fired the guy who said that thing. So again, we don't know exactly in which direction we are going. Like computers are becoming like almost humans. They have feelings. So we may possibly say in future, hey, don't use any swear word in front of the computer, computer has feelings too. So, but anyway, that's all kind of a stupidity which is going to happen once we move to that place. So again, so why it is called BERT? And the reason it's called BERT was because before BERT, there was another model came about, which is called ELMO. And ELMO came from University of Washington, which is based on bidirectional RNN LSTM. So they use the word ELMO. And ELMO is also one of the Sesame Street character. So suddenly people got very excited about it for some crazy reason. I mean, there is no reason to use Sesame Street character. What Sesame Street has to do with computer science and artificial intelligence? Nothing. But they following this. When this thing starts, it just goes on and on. So anyway, there came 2008, came BERT, and BERT basically stands for bidirectional encoder representation from transformers. And BERT also happens to be one of the Sesame Street characters, so it just became that. So what's so special about BERT? Suppose if I now have two sentences. This game is not fair. What does it mean? What is the word fair means? Okay, fair means that somebody is trying to cheat, looks like this is not fair. Okay, that's what the meaning is. Most of the humans can understand the meaning of that. But now suppose if I use another sentence, I had a great time at this fair. This fair basically means exhibition or some kind of an event. I had a great time at that fair. But the word is the same. How would a computer figure this out? This was $1 million question. How are you going to solve this problem? And that's what basically is being solved in BERT. Okay, after BERT, of course, there are a lot of different derivatives. On the GPCP side, they came up Grover. Why Grover? Because Grover is also one of the Sesame Street characters. Then also they have Ernie, and I think they just ran out of maybe Sesame Street characters, so that they don't have anything more. So then after that, another one very famous language model, of course, is Roberta, XLNet, and T5, and a few other ones also. There are a whole bunch of them. So these are all different language models basically that came about from BERT. And the foundation for all of these models was transformer. Okay, so now we're going to see how transformer will be used actually in trying to understand this problem or solving that problem. That means that if we have two words with a different meaning, how can we figure it out? Okay, so then we have GPT and BERT applications. As you know, in the case of GPT, we have machine translation or text generation. BERT also we have context-sensitive enhanced BERT embedding. And that is the focus of my talk today. Although it means a transformer is such a huge topic, it may possibly take me a few days to finish this whole thing. And in my CalTech course, I usually spend a lot of time just in transformer itself because it's a very, very wide topic. But today, my focus is going to be context-sensitive enhanced keyword embedding. Okay, so there are two things which happens in the English language. First one is called synonyms, and other one is called polysemy. So what is synonyms? Two separate words may have a same meaning. Okay, and polysemy basically means one word has two separate meanings. Okay, yeah. So polysemy is the one which creates a real headache for everybody, because now how are you going to handle that thing? So I'm going to read this sentence to you. Okay, this thing is being written actually by a lady, and she says that I banked on my husband. He was about to drop me to the bank. So the word first time they use bank means I depended upon my husband to drop me to a bank, which is a financial institution. So as you can see, we are speaking the word of polysemy. And he got late and I wanted to take a cab, but there was a taxi stop. So cab and taxi are synonyms. And then I ended up driving my husband's vehicle. It was showing low fuel warning. I had to go to the gas. So fuel and gas are no synonyms. Station to refill. By the time I reached the bank, car parking was full. So car again, as you can see, car and vehicle is the same thing. Cab and taxi, fuel and gas, these are all synonyms. But the polysemy is bank. Now, as far as the synonym is concerned, they are relatively easy to handle. The polysemy is the one that give us a headache, and that's what basically transformers can solve this problem for. Okay, so again, I've shown you the slide before. So now, as I said before, I went to a bank to deposit money. I mean to say a financial institution. Or if I say I went to a bank of a river to take a walk, so it means so bank here means a river. So that's the issue. So the question really is that how can we distinguish these two things? Of course, humans can figure it out. So how the system is going to figure it out? Just like the way humans figure it out. That is the key. We use all the words. We have to analyze all the words to understand the meaning of it. But since we can do it very quickly in our brain has got 100 billion neurons and we can figure it out. But how would a computer know these things? Using self-attention. That's the point which I'm trying to make here. Okay, so again, now how humans are going to figure this out? That I went to a bank to deposit money, and I went to a bank actually a bank of a river to take a walk. So just like the way humans are going to figure it out, we're going to apply the same technique for system to figure it out. So when we do is that we're going to create a self-attention. All words will be compared with other words. And then I'm going to show you the complete mathematics of that as well. And then it can figure it out. You can tell that exactly what the meaning is. So this is what we are. So BERT uses the concept of self-attention. Although I'm going to show you one very basic part of self-attention. But self-attention mechanism is way more complicated than what I'm going to show you. But I will actually give you some intuition exactly how the self-attention works. Okay, so that's what the whole idea. So now if I take the word bank and if I apply self-attention, I will get two separate embeddings. So let me first of all define what is an embedding. Embedding is that every word in the English language is being given a vector of some floating point numbers. And this concept basically came about in 2013 with word2vec by Thomas Michelov, his famous paper, word2vec. So now we can convert each and every word. So how many words are there in English language? Close to 1 million, okay? But we use 200,000 words most of the time. And most of the average people have a vocabulary of around 20,000 or 30,000 words, that's all. And so the thing is just that out of that, let's assume that we have 200,000 words in English language. Each and every word of the English language now will be converted into a vector of floating point numbers. And the vector size could be 200, 300, 500, 750. In the case of a bird, it is 750 floating point number. So those 750 floating point numbers represents what the meaning of the bank is. So that's so this thing basically started in 2013. So now let us look into word embeddings. Now, word embedding was actually produced by Thomas Michelov. Some of you might have heard about him. He's a very, very famous guy. And he started word2vec. And why? So what's so crazy about it? What's so crazy about converting every word into a floating point? Because now what we can do is this kind of a math. Now, suppose if I ask you, some of you might have heard about this example. It's a very, very famous example that if you take the vector of king, subtract man from it, and add woman, you will get a different vector. Okay, we are just doing some simple mathematics. Three vectors we are applying some kind of a mathematical function to that. So king minus man plus woman. And now if we compare the vector of queen with this new vector, you will see that the cosine distance is very small. We come very, very close to queen. So this was mind-boggling research at that time in 2013. So it means that we can convert every word of English language into a floating point vector. Okay, so first of all, they did that thing, with 200 floating point numbers, and they say, well, why stop at 200? Let's make it 300. It's going to become more accurate. 500, 750. So these things are called word embeddings. And when the first time when embeddings were being announced, people didn't believe it. As a matter of fact, just going to tell you a very funny story. Thomas Michelov, who used to work at Google Research, sent his paper on word embeddings to a conference. That paper was rejected because they said that it is impossible to do these things. You are doing something crazy. It was rejected by the conference people. So Michelov and Google guys got very angry at that conference people. They said, okay, here is the source code. I'm going to put the entire source code here on a GitHub page. You go and that source code was written in actually C++ languages. They were not using anything like Keras or TensorFlow at that time. He wrote everything in C++ and he gave that thing out. And say, you guys, you morons, didn't believe me? Here it is. Compile it yourself and figure it out. And that paper was published after it was being verified by a lot of people that whatever he is doing is correct. Okay, you can do this kind of a vector with words. So this was a mind-boggling thing happened. So Michelov basically used to work for Microsoft Research first. And then from Microsoft, he was there for 1 or 2 years. Then he moved to Google, where he published this very, 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 very famous paper. After that, he went to Facebook. He's doing the same thing over there. So again, he's working on this word to wake. But the problem with the word to wake vector is that it cannot solve the concept of polysemy. You have one embedding for a word. That's what the embedding is. That's it. You cannot change that thing based upon the context. So that's something which was done by actually by attention. Okay, so now when you look into this thing which is encoder and recorder, the first thing which you're going to see would be positional encoding. Because one of the things that we feed in our transformer is that we feed all the data in parallel. So if we are feeding, and then why do we need for in parallel? To improve the speed. Because in RNN, we used to feed the data one at a time. It is so slow. That's the old technology. But now if you're going to feed the data in parallel, so what is something that you need is positional encoding. Which word has come before which word? So that is something, first of all, we need to do. So positional encoding plus self-attention, we're going to give you a modified thing. Okay, now suppose if I give you these two words, work to live and live to work. They have a different meaning, isn't it? Some people say work to live, and some people say live. Words are the same, but the position of the words are important in English language, because otherwise the context will have a different meaning. Order matters. Okay, so that's what we need to do. This is what we need to do with a word. So we need there is a need for positional encoding. We all feed all the words at a time in parallel. So we need for a positional encoding. So it has two advantages. First of all, it decreases the training time, and long-term dependency of the words can also be handled properly. Okay, so this is the formula they use in the paper. Some of you have read that paper from Transformer paper. And this is what we have. So and again, actually it is not very complicated, but they just try to give you this formula, which is, they say that positional encoding is equal to position divided by 10,000 raised to the power of 2i divided by the size of the border. Okay, but don't worry about the mathematics part. That is very easy part of it. The important thing is that then we take the sine and cosine as the value of I is going to change. And this thing is very similar to writing any numbers in binary. Now we can take some number from 0 to 15 and we can write that data in binary. Okay, so what is 0? 0, 0, 0, 0. What is 1? 0, 0, 0, 1. And then what is 2? 0, 0, 1, 0, and so on and on. So the position of the 0 and 1 determines what the value is. Same thing is also true with our decimal system as well. We have numbers from 0 to 9, and we can put them in different order, the value changes basically. The idea is the same, but they use sine and cosine. And in my personal opinion, very likely with time, the sine and cosine thing will change because they made it just too complicated. Although it works, I'm not saying anything wrong with that. But there is a simpler approach too. Now, I'm sure somebody is going to come up with something better. So here we go. So I'm going to compute these positional encoding first of all in Excel. Some of you who may want to implement a transformer, because for transformer, there is no source code available. Transformer is just an idea. Everybody can write your own source code. Everybody can write the code for transformer. Like I have written it, and also at least hundreds of people have implemented the transformer. So if you are planning to do something of this time, you can first of all compute the positional encoding. So as you can see, first of all, you compute that formula. So the value of the positional encoding is that position divided by 10,000 raised to the power of 2i divided by the size of the border. And suppose my D model is 10, I can compute all of these numbers in Excel. Okay, and then I'm just going to take a sine and cosine values. Okay, so now as you can see, those are my values, and here I take sine, cosine, sine, cosine, sine, cosine, and here I'm not positional. Okay, so that's a positional encoding. Question?
Yes, the index. Well, what's the I stand for?
I stands for the size of the model. Okay, this is I going this direction. Okay, so
is it relevant to the sentence?
Yeah, it is sentence. So we define, this is based upon a D model of 10. Okay. And then I can take the D model of 512, which is basically being used. How big of a sentence you want. So this thing is just, so now what I will do is that here I've computed all the numbers in Excel. Now I'm going to compute all the numbers in Python. So in Python, of course, I'm using my D model 10. And here we go. This is my Python code. Very simple. 2 for loops are going, and bingo, I can compute it. And these are the values which I have computed in Excel, and these are the values which I have computed in Python. So as you can see, these values are matching. It's very, very, very simple, just like a one line of code. So this was not a big deal. But it is unnecessarily more complex. Although Google came up with this idea, but I think somebody should come up with some kind of a simpler approach to do this positional encoding. So, and then after that, you can just take the sine and cosine values in my Python code as well. As you can see in my Python code, I'm just taking the sine and cosine. And these values have been computed in Excel, and these are values have been computed in Python. And they are matching, of course. They're matching. Okay. So these are my positional encoding is being done. So now, of course, I can do my positional encoding with 10 values, and here are my values. And I can also plot the data. I can create a heat map for it. And with d is equal to 10, I can create a heat map. But now suppose if I take my model size to be 512, I can create another heat map. And some of you who might have seen some papers on transformers, you must have remembered this diagram. But you can generate this diagram all by yourself. When d is equal to 512, you will get this diagram. You generate the heat map for that. So a lot of people actually in the original transformer paper, this diagram was there. So this basically proves that the code which I've written for positional encoding is correct. Now let us focus on the main thing. This is the real beef. This is what self-attention. What is self-attention? So the self-attention works like this. So we take this positional encoding plus the embedding that we had before, add them together. Then we feed that into the self-attention, which I'm going to cover in the next few minutes. Okay. Then it goes to the feed-forward neural network, because then we have to train it. And based upon your training data, you train it, and don't think that this encoding, which is based upon the synonyms and also the polysemy, will be generated just by applying some mathematical function. No, we have to have some training data, and it goes through the neural network, and it goes through round and round and round and round and round, and the training takes place. Now, the training can take maybe for a few hours, maybe a few days, few weeks, depending upon how big of a training set you're going to have. And then you will see that embedding of the word bank will slightly change. Embedding of the bank used in different contexts is going to change slightly. Okay, and then it's going to reach at that point. So that's the way this theory basically works. Okay, so suppose let's take an example. Here I've got a simple sentence, which is called I am good. So now I have my 512 size embedding size. Okay, these are some random numbers which I've just thrown it in. Okay, so now I'm going to create 3 more matrices, which are WQ, WK, and WV. And in the beginning, the value of these 3 matrices will be some random numbers. And then during the training period, these values are going to become finalized. So right now, assume these values are totally random. So then we are going to create Q, K, and V matrix. So we have our X matrix, which is our original embedding. Do now the dot product with WQ. So here we have Q matrix equal to X dot WQ, and we're going to get 3 by 64 matrix. And we're going to get K matrix 3 by 64, and V matrix, which is 3 by 64. And then we create our Q, K, and V matrix, which we saw before, like using these things. And then after that, we apply the self-attention. Now we are coming to the root of the problem. So now what we are going to do is that compute Q, K, T transpose. Okay. So my Q is 3 by 64, K is 3 by 64, and the transpose of K would be 64 by 3. So now if I multiply Q, K transpose, what I will get is 3 by 3 matrix. This is my self-attention. But it is currently based upon the random values of those three things that we have. WK, WB, and WK, Q, and B. Now, once this thing is again, so this is my self-attention. This shows that the word I is mostly related to the word I, and am related to the word am, and good related to the word good here, because there is no polysum in this example. If the word, if I use the same other example of using the word, I went to the bank to deposit money, you will see that now the word bank is related to money. Isn't that the way we figure it out as humans? When I tell you, I went to the bank to deposit money, you immediately say, hey, bank is that bank, okay? Because money and bank are related. And this matrix is called self-attention matrix. Okay.
Yeah, fine.
Okay, we have got 5 more minutes to go, so I'm just going to finish this whole thing very quickly. Okay, so here we have, so as you can see, this is what we have. I went to a bank to deposit money, and here now using the self-attention matrix, we can compute these things. Okay, and similar. So that's what it is. So now we can, and then just to normalize it, we can also normalize this data by dividing this whole thing by 64. I don't know why the 64 is not showing up here. These values have been, I think it is not displaying the equations, mathematical equations. Sorry. There should be actually under root of 64 here, and then we take the softmax function for it. So all these, oh my gosh, all these numbers are gone. But anyway, see, in PowerPoint, we have something which is called equation feature. Some of you might use it. All of people who are using mathematics use these things. But sometimes you display it, it won't show up. It was showing up in my home computer, but this is a USC computer, so I don't have any control over it. But anyway, that's not an important. Important thing is that finally, when you compute this step 4 of self-attention matrix, and here we're going to get these things. So here are my modified. Here I'm going to have my modified embeddings. That's the point which I'm trying to make. I think I'm got 5 minutes left, and that's all basically I wanted to say. Is that self-attention is a way by which I can change the embedding of my words based upon the context where it is used. And this method of doing it is identical to the way humans interpret the words. We are getting one step closer to making a real robot which can understand polysynthesis. Okay, we can understand that. And that's what it is. So, and then how do you go after that? It means that once you create these modified embeddings, then you do the masking approach. Like in your sentence, remove some of the words. And the goal remains to be to predict what these new words are. So now it becomes a neural network. Now the neural network will go on and on and on. Now, of course, I have trained this thing with only 15 sentences. Then my embeddings are not going to change that much. Suppose my embedding of the word bank was, let's assume just a one number, 10. It is going to change to 11 or 13 depending upon the reference in which we are taking. But now suppose if I take a huge training set data, then you will see that slowly embeddings will start changing of these words. So now we can understand that the word bank is being used in which reference. So based upon the self-attention mechanism which is there, we have the ability now to understand the meaning of the word. So this is the training of the neural network happens, training data, we compute Q, K, and B, which has been trained, and then of course we get the modified. Okay, so now this is the way BERT figures it out. So that is the crux of my talk. So now BERT can understand when I say I went to a bank to deposit money and I went to a bank to bank of a river to take a walk. So that is a way basically transformer embedding.